when this application is running on its own and nothing else is running on the processor, it runs very regularly, about 17 million cycles, whatever that is in units. But now we've done an experiment where in our reference application still runs alone on the core. There's no dependency on anything else, except that on the other cores we put pieces of software that generates interference just because are using and competing for resources. And we call these rapid demons. Rapid demons here comes from the demonic adversary, the principle from cybersecurity of trying to break something. And how do you break in? So these rapid demons are very carefully, but very simple pieces of code that will use a particular resource. But in that particular case could be level 1 cache, level 2. If then we rerun the same application, doing exactly the same thing as before with the same input data, but now there are other programs running on the other cores, we not only see an increase on the execution time, but also a spread of the distribution. And to the careful eye, the execution time of that application has almost doubled. And it's doubled not because there are dependencies, it's just because there's contention on shared resources. So what the multi-core certification challenge is to be able to provide complete assurance to demonstrate that we understand all sources of interference, and therefore the method that we're using for determining the execution time of applications and to determine whether they meet the timing requirements is robust and solid. You probably know why is the use of multi-core processors is happening now and not before, but different industries have, or different areas of the industry have different requirements. One is the reduction of the improvements in size, weight, and power. Let's say eVTOLs or light aircraft, they just cannot afford very heavy racks of computers, and therefore putting all computation in a device that has maybe half a kilogram of weight, even less. It's very attractive, but it's also the challenge of not being able to have availability of single core processors. You basically cannot buy them because chip manufacturers and board manufacturers are moving to providing multiple board computers. So moving to slide number 9, the reason why I like to put this description, this slide, is to explain why we cannot do what's coming next is not business as usual. There is a tendency that when a project is successful, it goes through certification, and then there's a new iteration, there is a technology upgrade, well, it worked okay doing activity X on the previous project. Why cannot we do it applied again? And timing analysis, which is the ultimate objective of CAS 32A or AMC 2193, is a very different beast from the times of deterministic CPUs, let's say a 68 or 20, where every instruction takes a fixed number of cycles. You can basically count it with a pen, with a piece of paper, a pencil. So making the timing analysis on these old processors can be tedious, but it still is very realizable. Processors have moved to be what I called predictable, where they are a bit complex, they maybe have some limited cache, but they still are under the realm of I can count how many cycles a particular number of instructions that execute. The limit was brought to the next level when I call it category 3 or known unpredictability, where that could be systems would have a couple of speculative executions. There's more predictability, a couple of levels of caches, for example, which they are under the grasp that we still could be able to count things. It's just that is a bit more difficult. Multi-cores is a chasm. Multi-core processors now at a stage where they are well beyond the known unpredictability, and there's a lot of what I called unknown unpredictability. There are interactions which is a priori is extremely difficult or extremely pathological to understand. And that could be issues related to out-of-order executions, cache coherency protocols, lots of hidden features of the processes that are even documented but very difficult to find, plus a lot of optimizations that these chips are mainly designed for average case behavior and make the worst case extremely difficult. So unfortunately, time and the business as usual is not possible. And for this reason, CAS32A, and then first derived from CAS32, was produced by the academia, by the industry, as a set of objectives and rules to determine what activities, what objectives do you need to satisfy to make sure that you understand the multicore platform, and therefore the assessment of whether you satisfy your timing requirements is robust. CAS32A was the cast paper that has been now adopted as an AMC or EASA as a 2193, and the FAA is expected to be released again very soon. They are basically the same. There are some clarifications that are worth noting, but for all terms and purposes, the objectives are the same. We've done plenty of a few other seminars, webinars explaining what are the different objectives, but just one slide only to explain what are the overarching principles of these objectives. There are two objectives that determine what are you planning objectives, or how do you extend your PSAC and PHAC planning objectives to describe what is the multicore platform and how you're going to verify it and how you're going to achieve all the rest of the objectives. There are two objectives that relate to the identification of critical configuration settings. Any setting of the platform that if it's changed can impact the execution time is called a critical configuration setting. And it's essential to track that all the analysis that's been performed is for that particular configuration. And this is where any analysis which is not on the final configuration or very close to the final configuration is much weaker or even not acceptable. Then the next two objectives are MCP resource usage 3 and 4 are about identifying the interference channels and that the platform has enough capacity on the available resources to deliver to satisfy the computational requirements that your application requires. Now, you may notice that objectives in yellow apply only to DAL A and B. The rest apply to, the objectives in white are the only ones that apply to A, B, and C. And then if your system is DAL A or B, it also has to do the yellow ones. However, a level of interference channel analysis is required even for DAL C level. And this is because the objective of how you're doing worst case execution time depends on understanding what are the different sources of interference. The only difference perhaps is for DAL A and B, you need to answer the question that you know all interference channels. For DAL C, maybe that all can be done in lowercase letters, or at least most of them. Final objective is, the key ultimate thing is calculation of worst case execution time, which is objective MCP software 1, and data coupling, coupling, a wider objective that already exists in the DO-178C on data coupling, coupling, which is software 2. And then the other key part as well is, if all else fails, and there's something that we haven't that behaves as unexpected, there is the need of having a safety net that identifies that either the configuration is changed or the timing requirements had not been satisfied and has been caught. So within that context, we as Rapita, we spent the last 5, 6, 7 years working very intensely in producing a solution on the certification of multi-core processes following the objectives of AMC 2193. And a combination of the solution is tools and services and documentations and processes. We name all this package of things MAC 178 as a multi-core avionics certification for high integrity systems. And what MAC 178 is a cert pack. Basically, is a collection of certification artifacts, processes, templates, procedures, checklists that implement a systematic and detailed process of all the activities that need to be performed even with independence, and all the reviews and checklists that show independence, to provide a systematic way of identifying critical configuration settings, interference channels, and characterizing those interference channels. And what we're going to do today is to talk a bit of one of those aspects, which is interference channels. What interference channels, how they can characterize them. But the data that we produced on the examples today is part of what we called our blueprint, which is a sample cert pack that people use as a way of understanding how does a cert pack for a multi-core DO-178C project or A2103, how does it look like? We pick some of the examples on this document, and this is what is going to be produced later on in the presentation. Just another two small things, additional things to finish off. One is the components or the activities that are required to do a multi-core certification can be split into main two branches. One is the middle one we call platform, is hardware. There is, you need to understand the hardware, and that hardware means a lot of a paper exercise to look at data sheets and features of how that platform is being configured, basically understanding the documentation of that platform. And then testing, we call it characterization of give me the evidence that demonstrates, that shows what is the impact of that particular platform. For example, what is the impact of a cache hit or cache miss in timing. Once you understand the platform, then you can understand the software. Because now we understand what are the things that the platform does that may affect the software, and exactly in the same way, there is an activity to understand the high-level structure of the software architecture, what are the timing requirements, and then perform the worst-case execution time under stress conditions, under the impact of different interference channels, to be able to determine what is the execution time of the application in worst-case conditions, worst-case interference, and that is the software. But then, in order to do this, there's a tooling support. This work is very laborious, so tooling is a way of being able to automatically produce and reproduce results. We call that as an integration activity of integrating tools and rapid events. There is, and in order to perform all the activities in a systematic way, there is a planning part that is an integral component of any DO-178C project, which is the application of processes and generating the evidence that these activities are being performed. And then finally, is everything we do is with an emphasis on presenting a successful certification argument. So certification considerations are always in the mind of any activity. So we are talking today on the kind of activities you would do on a pilot phase, an early discovery. We then like to structure this into an implementation phase, which is then you actually go for it. Any issues that are found, for example, applications that they don't meet the timing requirements, may require a re-architecture of the software, some optimizations, or some changes of configurations to enable or disable some devices. Reanalysis. Once that implementation is done, we have now a system that we know is complete or certifiable, and that's when we move to a certification phase, which is dotting the I's, crossing the T's, checking all the traceability, checking all the generating all the qualification kits of all the toolings involved in the process, and then producing the final run first score. Now, on that note, this is a very high-level overview of what is Mag 178. I'm just going to pass the token to my colleague Carl. Thank you, Carl, for jumping on cue to go through this process, in particular focusing on interference channels. Carl. Oh, yeah.
Thank you very much. Yes, like Ian's just said, I'm going to go back into starting from the beginning, some more details as to what interference is and what we would classify as an interference channel. And finally, I'll go into some examples, some worked examples from our blueprint project, including measurement strategies and how we can approach bringing it all together for certification. So first things first, let's start with going back to basics and start with the task running in isolation on a core. And like Ian earlier stated, this was what we'd consider a complexity 3 or below system where the execution time is calculable and measurable, and see what happens when we put that into a multi-core context. So in a multi-core context, we might have a second core or a dual core system, and we'll have an independent task that we can place onto that second core. And we might see that our execution time of our original task on core 0 does increase somewhat. Now, obviously, execution time increasing somewhat for arbitrary or unknown reasons is a scary principle and a scary prospect when it comes to meeting deadlines. So the next thing we need to do is explore why that could happen. So what we have in various tasks are particular regions that we can call sensitive or aggressive areas of a task where, for example, a particular resource might be used heavily, and the task might be particularly sensitive or aggressive at using that resource. And we'll go into that a bit later as to exactly what that means. On the whole, in this case originally, we've marked some sensitive and aggressive areas that happen to not overlap, in which situation you might see that there's not much of an execution time increase. In the case where they do happen to overlap, you might find that the execution time actually increases drastically. We've seen percentages from 10% to 1,000%. But we need to obviously understand why this is happening, how this is happening, and where this comes from. But effectively, this contention for resources can cause execution time increases of an arbitrary amount. That's what we class as interference. It impacts the execution time. And there are other things that are associated with that, but let's just go for the simple case for now. So an interference channel then is, as Guillaume already mentioned, defined in AMC 2193 as a platform property that can cause interference between software applications or tasks. So if we've just shown that interference is the phenomena where execution time can be impacted, we're now looking for platform properties that can cause this interference to occur between our software applications or our task. So how do we split these up? We can effectively, and this is an internal Rapita definition, but it can help a lot for putting interference channels into context and helping to understand and find them in the first place. But first we can look at some of the more approachable examples, which are the direct interference channels. And we can look for example, quite simple contention exercises. For example, on an interconnect, we can have multiple different cores attempting to do things on this interconnect and getting in each other's way, or competition for cache. Both of those examples we will look at in a little bit more detail in a minute with some graphics to make it a bit more approachable. Other accesses to memory in the same way, things where there's direct contention for resources, quite simple to see. Next, we have indirect interference channels, which can be slightly harder to see or understand, or as we see later, to attempt to measure. where the execution time of a task can be impacted by unpredictability in the hardware. For example, in a routing for an interconnect, for example, on the LX2160A, we have a ring buffer, and the routing through that ring buffer can be determined based on the traffic. So if the traffic is particularly heavy between some devices, it might cause other traffic through the ring buffer to reroute, hence causing potential interference through and execution time increases. Otherwise, there can be variability in memory accesses, or another example that I'll briefly touch on later as well, cache coherency protocols, for example, with the introduction of shared caches between different cores and the introduction, therefore, of the potential of shared data between the private caches of or shared caches that are partitioned from the individual cores. There must be some coherency protocols which will often get in the way. For example, in the NXPT series, we have snoops, which are always serviced first because cache coherency protocols must be serviced first to ensure that no stale data is used in any execution behaviors. That can be potentially even blocking for a core not to be able to access its local cache due to servicing too many snoop requests. The other most scary, especially in the aerospace context, interference channels are the unknown interference channels, the ones that you generally can't find through analysis of TRMs or source material, and are generally only found during actual testing or analysis of other interference channels. And this can be anything from a silicon bug to, which we have found, to, for example, on the P4080, an imbalance in the bus arbitration for each core, where core 0 happens to be benefited by being allowed to make bus transaction when there is heavy interference generated on all cores, preferentially compared to the other cores. Not documented anywhere, it just happens to be a feature that we found during testing. Other things could be clock frequency slows from DVFS, which can and should be disabled, but even when it is, we have seen effects where thermal throttling occurs and frequency gets reduced, despite configuration settings being set not to allow this. Again, other undocumented behavior and potentially silicon bugs. We have not yet come across a project where we haven't found an unknown interference channel. And so this is something you would expect to see, and something a cert authority would also expect to see somewhere in your documentation, that something unexpected happened. So now that we've looked at some of these, let's go into some worked examples to again bring it back to a simple level so we can build it up to be a bit more complicated. So we have here an 8-core system with various levels of cache, and we can imagine that when in isolation, core 0 wants to make accesses to the L3, it can do so with full bandwidth and with all available resources, and that when cores 1 to 7 also feel like they need to make accesses to L3, there'll be multiple potential interference channels along the memory hierarchy that are exercised. Specifically, we're looking here at, for example, bandwidth contention for L3. So there'll be numerous queues and buffers within L3 to allow memory to be accessed, or read or written. There'll only be a certain amount of bandwidth that these queues and buffers have, and these will be contended for by the other cores in this case, along with various interconnects along the way. For example, another example would be if we just look at, for example, 2 cores. We don't need to make it all 8 to make it complicated. We might have a cache eviction example where L3 is shared between all cores. And for example, core 0 wants to place data in L3. In isolation, it would be able to access this, and it would know that it was there or guarantee that it was there unless it overwrites it itself. However, it might be that core 1 can place data in L3 also and evict some of the data that core 0 placed there in the first place. Obviously, this might then cause a cache miss when core 0 attempts to read this data again, forcing it to fetch it from DDR, which might have a much higher latency and an overhead. Therefore, in a pathological case, if this happens for every access, that could be a massive increase to execution time. Another one, which is hard to show in a graphical sense, would be the cache coherency protocol that we just discussed, where the snoops from actions to a shared piece of shared memory may impact a core's ability to access its own cache when the mechanism effectively blocks it because snoops have to be serviced first. So I've given some simple, reasonably simple examples of what some interference channels might be. I'm going to go into a bit more of a complicated one in being able to demonstrate how we might go about measuring some multicore interference, and then show some results data. I am conscious of the time. Just to quickly bring this back to the original point that Guillaume was making, where we need to associate all our processes and evidence with MPC resource usage 3 and 4 for the AMC 2193. We've had a look at identifying some interference channels or having a look at what they are. We need to go about characterizing them and understanding their timing behavior and resource usage behavior before we can start beginning to characterize our software on a given platform. So the characterization of the interference channels then. The maximum impact of the interference channel is what we want to understand. We want to understand what is the worst case for interference impacting my software later on. So we need to understand what is an individual interference channel's maximum potential for interference. So for that, we need to understand a very small, very basic piece of code that will have a very predictable behavior that we can run under no interference. So for this, we have something that we call rapid daemons, like it's already been introduced. And in this case, what we want is something called a victim rapid daemon, which is particularly sensitive to whichever interference channel we are attempting to stress in a given time. For example, in a bandwidth sense, a sensitive rapid daemon would be making as many accesses to an interconnect as possible, for example, which would, with interference, you would assume, be limited to the maximum effect. In this case, we also need an aggressive rapid daemon to run on the other cores to generate that interference. In the case of the bandwidth, for example, the aggressive rapid daemon and the sensitive rapid daemon might be one and the same. We may find that while we are measuring the impact on core 0, the rapid daemon on cores 1 to 3 are the same. However, they might be different, and for different interference channels, we will obviously need different rapid daemons that service those particular interference effects. Once we have generated some data from the test scenarios that are effectively running the victim rapid daemon in isolation and understanding exactly the timing impacts or timing behaviors and resource usage behaviors, we will then run the aggressive rapid daemons on 1, 2, and 3 cores and expect to see execution time increase if the interference channel is indeed a problematic one. We have seen interference channels that have no impact, and later we will see that not all interference channels are behave linearly. That is to say, 1 rapid daemon and 2 rapid daemons do not necessarily constitute the same impact difference on the execution time as 3 rapid daemons do. So going now to an example that I promised, we're looking at the T1040, and this is from the Blueprint project, which is the platform that we used for that, and a particular interference channel, which is in this case the DDR memory controller. So this is what our interference channel might look like. We have identified it, and for traceability purposes that I won't go into because we're not talking about MAC 178 in detail, we're only talking about interference channels. We have an identifier of the resource that it applies to, and in summary, this interference channel is effectively the serialization of requests from multiple sources within the DDR controller. Now, you can read this at your leisure during the recording of it if you wish. It's not as simple as it sounds, but effectively the serialization of various accesses can, within the controller, be handled in unpredictable ways based on how it thinks the most efficient method would be, that is, grouping or reordering the accesses. We've got some mitigation recommendations. Again, mitigation is something we won't have time to speak about today, but it's another interesting topic and would do for a whole seminar, if not a week of discussion and training. So now that we have an interference channel that we're trying to characterize or trying to measure the impacts of, we must now design a sensitive rapid daemon and aggressive rapid daemon to maximize this interference and to maximize the effects that can be seen by this interference. So in this case, we need to be able to develop a Rapidemon that is as sensitive as possible to inefficient memory accesses. That is to say, we don't want it to be able to be optimized away by the memory controller or grouped. We want it to be effectively bottom of the pile of priorities because it will never be an optimal access pattern. And accordingly, with the aggressive interference generators, we want to effectively group the accesses it makes to be efficient and ideally kick out or deprioritize the accesses made by the sensitive Rapidemon. So as you can see here, we have our sensitive, I just realized you can't see my mouse. We have the sensitive Rapidemon on core 0, which is our application, and the aggressive Rapidemons running on core 1, 2, and 3. The reason this is slightly more complicated is because obviously we have, in the case of the T1040, a memory hierarchy before the DDR that we need to miss L1, we need to miss L2 before we can hit DDR. So while the Rapidemons are essentially simple snippets of code, confirming and verifying that they actually function correctly and do what they say is a complicated process, and accordingly they are qualified. So to understand what the Rapidemon is doing, we need to not just measure timing impacts and to understand the impact of the interference channel. We also need to measure various resource usage metrics, which we can do using hardware event monitors. In this case, useful metrics to read would be the L2 data cache hits, the DDR reads, and the DDR row closures. And I'll show some of those in the results that I show. So now that we know what our aggressive and sensitive Rapidemons are that we require to characterize this interference channel, we can construct a test, and this is an excerpt, a screenshot from our test configuration editor within RVS, which has at the top the metadata, which is not functional whatsoever, but does allow us to trace through our test design and our interference channels all the way through to our results, which is an essential part of Mac 178 as a whole, along with our metric groups, which are the metrics we require to measure or to collect whenever we do our tests. These need to be grouped because there are only a certain number, in this case on the T1040, 6 metrics that can be read in one go. And the test configuration editor allows us to select any number of metrics and group them in any way and be able to run the test on a button click repeatedly. So the test scenarios themselves, we have in this case one contender. We have first actually the baseline, the baseline which has only the contender, which is in this case the sensitive Rapidemon running on core 0. So we get a baseline in isolation effectively of how the Rapidemon functions and what the timing behaviors are. We expect this to be very tight because the Rapidemon is intentionally written as a very simple piece of code, which is very predictable. So we expect it to be a very tight timing behavior and very easy to baseline the differences in interference on. So then we have one contender on core 1, which is an aggressive Rapidemon. Then, as you can see, on 1, 2, and 3, and then on 1 and 2, and then on 1, 2, and 3, so that we can understand the differences in timing behavior for different levels of interference. And now the truly interesting bit from my perspective as an engineer is the results to analyze. So we see here that we have 3 different effectively groupings of timing behaviors. So the first in green would be the baseline. So that's the very tight timing results that we expect from the Rapidemon, the sensitive Rapidemon running in isolation. Next, we can see that there's the red bar, which is the timing behavior of the Rapidemon, the sensitive Rapidemon, when there is one aggressive Rapidemon effectively making suboptimal or as maximizingly suboptimal accesses to DDR as possible. As you can see, the timing behavior is still rather tight. And interestingly, when you add 2 Rapidemons, the timing behavior, the variability, that is, of execution time actually increases a huge amount, as well as the actual execution time itself. And as you can see, with 3 Rapidemons running, 3 aggressive Rapidemons running in contention with a sensitive Rapidemon, we actually maximize our interference in total that we have available with our 4 cores. And we see a much larger variation in execution time, along with obviously a much higher execution time at all. Now, this is obviously generated using RVS suite, tool suite, which allows us to make these tests reproducible and simple, and we can also analyze them to a bit more detail. For example, I've spoken about using the isolation test as a baseline. So in this case, the tests are actually baselined on this isolation. So we see now that we have percentage increases. If you look in the second row in the table, which is the first scenario with one rapid daemon running, or in the red in the graph is in the histogram, we see that we have a roughly 3% increase in execution time with only one rapid daemon running, which might be a very acceptable amount if that's something you can build into your engineering margin. With two rapid daemons running, we have around 7%. In the worst case, potentially 9%. And in the third case, in the third test, we have around 16% on average, 19% in the worst case that we observed in these 2,000 tests. And interestingly, if you look into the table a little bit lower down, you can actually see the results of the metrics that we calculated. So that we gathered, sorry, not calculated. In this case, these are all actually counted metrics, not derived in any way. So the L2 cache data accesses, for example, you can see have remained very stable the entire time. That means that our victim is making a very predictable amount of L2 cache data accesses, which we expect as we wish it to have no hits, no changes in our behavior. So these are some ways that we can confirm that our rapid daemons are doing the correct thing and that we are testing the interference channel we think we are testing, which is actually one of the most important parts of how rapid daemons are designed, because we need to be very sure that we are stressing the interference channel that we think we are stressing. Actually, the evidence that goes along with that can be very difficult to generate. Right, so I'll move on to an example that almost acts as a wake-up call for if you think you understand how predictable interference channel can be. No, they can be completely unpredictable in terms of one rapid daemon, in this case being the red bars, adding a certain amount of interference, call it 7-8%. The second one, i.e. 2 rapid daemons running in contention on a 4-core system, again being a predictable roughly 7%-8% increase, and then a third rapid daemon, whether it hits a threshold of some sort or generates some unexpected behaviors, suddenly has a 100% increase in timing behavior. And again, you can see that there's an increase in variability, which is something that always comes along with interference effects, an increase in the variability of execution time as well as the increase in execution time. Hopefully it all comes together a little bit, that you can see what the identification, characterization, and later the software characterization steps are.
The first question was from Sims and says, could you talk more about how the daemon programs are written and what resources they contend for? I think that was from before you actually explained rapid daemons, but just in case, could you provide a bit more information on what is the process that we go through to specify and write rapid daemons?
Yeah, of course. So first, we obviously identify an interference channel, and we understand what we can about the interference channel and the resources that it involves. And we effectively try then to understand what we need to do, what exactly we need to target to produce the maximum amount of interference on that resource. Because obviously an interference channel is very specific to a resource, and obviously we might need to, like I said before, miss other, for example, in the memory hierarchy, miss other resources to get there. The answer is it's very tricky. It requires effectively the requirements to be written based on the interference channel and how we think it can be best stressed, and then testing and confirmation of those. Does that answer your question?
Perhaps you could, related to another comment later on, the use of performance monitoring counters or hardware event monitors for the verification of the behavior.
Well, first we have to verify that the hardware event monitors actually do what they say. We've seen all sorts of behaviors of hardware event monitors not doing what they say they should do, counting random numbers, counting numbers we don't understand, counting twice for each number. So their first step would be to verify the hardware event monitor behavior at all. which can again be an arduous process of creating the tests to do that, and then obviously performing the verification process.
Thank you. There's another question from Bikash. It's also very related. It says, could you tell us more about how aggressive Rapidemon is created to accept maximum interference for the victim?
So we attempt to generate or create a Rapidemon that, in as few instructions as possible, creates as much interference as possible. That is to say, we want to generate as much interference as possible per instruction that we issue. It really depends on the interference channel that we're talking about. For example, for something simpler like bandwidth or cache accesses, it's as simple as just issuing cache instructions that, for example, hit a particular cache as often as possible. That might relate to the architecture of the cache itself to ensure that we always hit something that is in the cache with the minimal subset as possible, so have the least overhead possible. That can be a lot more complicated for peripherals or devices that aren't quite as well known or well documented. A lot of it requires good documentation and understanding of the platform itself.
Thank you. Thank you. Another related question is, what are the mitigation strategies and how can you use the Rapidemons to demonstrate whether mitigation strategy is effective?
Well, the mitigation strategies we often determine either during the interference channel identification or during the critical configuration settings analysis, which we often do in parallel. And they can be anything from disabling a certain device. For example, if you want to avoid your L2 cache interference channels, you might decide you want to disable the L2 cache. That may do what you expect. And you would still have to verify that by effectively still testing the interference channels in question and seeing that they no longer are in effect. If you have some interference channels that cannot be fully mitigated, for example, the one we were speaking about earlier might not be fully mitigatable if you're using DDR. However, you could disable any, for example, functionality or reduce interference by disabling some functionality. You would then have to show that this interference channel is exercised by your Rapidemon still. So the design would be the same, and you have to then see in terms of execution, time or resource usage in the same way as before, to determine that the effect is effectively mitigated, that the interference effect is mitigated, again, with the same maximizing interference Rapidemons and your sensitive Rapidemon in the same testing mechanism.
In your slide 48, that could be, for example, the mitigation could be that we know that this extreme behavior only happens when the 4 cores are active. So one of the mitigations could be,
if we go back
you're
to
only allowed to have 3 cores active, and therefore you are on the boundary of the 10-20% interference.
Yep, absolutely. That would be, for example, an approach. There are some interference channels that might not be fully mitigatable, and you still have to, obviously verify the level of mitigation you've achieved.
Okay, very good. So there's a couple of extra questions. There is coming from Sims. I believe you have an academic version of the Rapida tool suite available for research. Are Rapidemons included in that? I may answer that question. The answer is unfortunately not. The academic version is only of our tooling themselves. Rapidemons are part of our, we call the Mac 178 and the Blueprint package. But we also are interested in working with academia to support the advances research and understanding on these aspects. So come and send us an email, Sims. Yeah, good to see you here again. There's a final one for you, Carl. It says from Vikash, what can we conclude from the distribution graph? can we say that the more the core on the platform executes and contends for resources simultaneously, the longer worst case execution time for the victim application?
So in this case, we are actually only stressing one interference channel, being this DDR controller interference channel. So we can't necessarily yet make any conclusions about the platform or as a whole. We have to obviously do this process for all interference channels and find a way to bring all that together to create an argument that we've understood what the potential worst case impact on our software could be, and then do a similar approach that we have now, where we've used the victim Rapidemon to basically demonstrate what the timing behavior of the interference channel would be. We have to do that then for our software. Does that answer the question?
Yes, I think the answer is yes, but sometimes we've seen some strange things happening.
That's always the answer. There's always something strange happening.
Where with an extra Rapidemon, things happen to go faster, not slower.
Yes, that's something important to realize as well, is that obviously you've got your aggressive Rapidemons, and with some, I'm just going to go back to the bandwidth interference channel, where you have a certain amount of bandwidth available on your interconnect, and your aggressive Rapidemon might just put as much traffic on that interconnect as possible. If you have two of those Rapidemons or multiple of those Rapidemons running, they will be interfering with each other as well. They will be limiting each other's impacts and interfering with each other. So it might be that you have a maximum worst case in that sense. So you might not see any increase anymore when you add a third or fourth Rapidemon, depending on your configuration. It might be that, like Guillaume said, we have actually, in very, very rare cases, seen a speed up with an additional Rapidemon. So in the general case, yes, the worst case execution time goes up when Rapidemons are added. In some strange cases, it depends.